Continuing physical chemistry, chapter 9, section 2, we're going to talk about partial molar quantities. Okay, now let's say we have n subscript 1, and that'll be the number of moles of substance 1, and then n subscript 2, that'll be the number of moles of subscript 2, etc., to n subscript r, that'd be the number of moles of substance r. So if you have r different substances. Now we're going to say let Vm star be the molar volume of the pure substance. In other words, before we mix it, put in a solution. Now remember, this is different than star before. We used star to say it was like temperature dependent. Now we're saying star means pure substance in this chapter. Or we're going to have a collection of pure substances before they get mixed. So V star will be the total volume of all the substances before they're mixed into a solution. So V star would be just the number of moles of substance 1 times the unmixed molar volume of substance 1 plus the number of moles of substance 2 times the unmixed molar volume of substance 2, etc., all the way to the number of moles of substance R times the molar volume, unmixed molar volume of substance R. Then we're just going to use plain V to be the total volume of the solution after mixing all the different materials. So even at constant temperature and pressure, the volume is not necessarily equal to the unmixed volume. For example, let's say we have 50 milliliters of ethanol and 50 milliliters of water. Then the unmixed volume is going to be 100 milliliters because 50 plus 50 is 100. But the actual volume is just 96.5 milliliters. You probably heard that example when you took general chemistry. Now V cannot be greater than V star because of the different types of intermolecular forces and the size and shape. It just wouldn't work out. Now, there are other extensive quantities we've learned before. S for entropy, G for Gibbs free energy, H for enthalpy, A for etc., U for internal energy. So remember, we could write volume as a function of the temperature and the pressure and the number of moles of substance 1, the number of moles of substance 2, etc., to the number of moles of substance R. And likewise, we could write the Gibbs free energy as a function of the temperature, pressure, number of moles of substance 1, number of moles of substance 2, etc., all the way to number of moles of substance R, if we have R substances. Now we're going to write the differential form of V. So we have the differential of volume is going to be the partial derivative of volume with respect to T, holding everything else constant, times the differential of T, plus the partial derivative of volume with respect to pressure, holding temperature and everything else constant, times the differential of pressure, plus the number of moles of the partial derivative of volume with respect to the number of moles of substance 1, holding temperature, pressure, and all the other substances constant, etc., times the differential of the number of moles of substance 1, etc., all the way to the partial derivative of volume with respect to the number of moles of substance R, holding temperature and pressure and all the other substances constant, times the differential of the number of moles of substance R. Now we're going to define this V sub j with a line over it as the partial derivative. So this is partial molar volume of J. So the partial derivative of volume with respect to the number of moles of substance J, holding temperature, pressure, and all the other substances not equal. So we say this is the partial molar volume of substance J. Now in other books, be careful of the nomenclature because different books, they have different symbology. In other books, they might use this symbol to mean just molar volume, which would be just the total volume divided by the number of moles. So the differential of volume is, remember, equal to the partial derivative of volume with respect to temperature, holding pressure and all the substances constant, times the differential of temperature, plus the partial derivative of volume with respect to pressure, holding temperature and all the other substances constant, times the differential of pressure, plus, and then we can do it in summation notation, saying the sum over substance I of the partial molar volume of substance I times the differential of the number of moles of substance I. So we can write the partial molar volume of substance I is equal to a function, of temperature, pressure, number of moles of substance 1, number of moles of substance 2, etc., all the way to the number of moles of substance R if we have R substances. Now let's say that we're going to have constant temperature and pressure, so that the differential of temperature is equal to 0 and the differential of pressure is equal to 0. So then we get the derivative of volume is just equal to partial number of, or the partial molar volume of substance J times the differential of number of moles of substance J. But that's just for that one component when that it is added. So here's a graph of the volume divided by centimeters cubed to cancel out. So we make it unitless. So it's volume versus the number of moles, in this case magnesium sulfate per mole. So this V is the total volume here of the solution, and then the partial molar volume of substance J would be the slope. So as you can see, it starts out here. As it increases, for a while the slope is negative, but it gets less negative. There's a point here where it's 0, and then as you keep increasing, it goes up again. So the slope of the tangent line is going at any point here is going to be the differential of the volume divided by the differential of the number of moles of substance J. So the derivative of volume with respect to the substance J. And that's basically the partial molar volume of substance J. Now let's look at our nomenclature again. So we have V star of pure substance. Remember, this is the total volume before mixing. So in summation notation, it's the sum over all substances I at the number of moles of substance I times the partial molar volume of substance I, unmixed. But then the total volume after mixing, we get volume is equal to the sum over all substances I at the number of moles of substance I times the molar volume, partial molar. Oh yeah, no, just the molar volume, substance I. So that's the difference between unmixed and mixed here. The star means unmixed, remember. So the volume could also be written as the sum over substances I, the number of moles of substance I, times the partial molar volume of substance I. So the change in internal energy from mixing, oh no, sorry, that's a V. So the change in the volume from mixing is going to be the actual volume minus the initial volume. The total volume after mixing minus the total volume before mixing. So substituting that in, we get the sum over number of moles of substance I times the partial molar volume of substance I minus the sum over substance I, obviously, by default. The number of moles of substance I times the unmixed partial molar volume substance I. And that is just distributing through. Then you get the sum over substance I, the number of moles of substance I, the partial molar volume of substance I, minus the unmixed partial molar volume of substance I. So the change in molar volume from mixing is equal to the sum, the I is, implied here, number of moles of substance I, the partial molar volume of substance I, the molar volume of substance I minus the unmixed molar volume of substance I. Okay, and that's, of course, that's assuming we said constant temperature and pressure, so those terms dropped out. Now, like I said, the volume is going to be less than the unmixed volume, but that's only if you're assuming constant temperature and pressure, of course. Now, likewise, we can do the same thing for U subscript I with a line over it. That will be the partial molar internal energy. Or we could do the same thing for H subscript I, and that's going to be the partial molar enthalpy. Likewise, okay, so the partial molar internal energy of substance I is going to be defined as the partial derivative of the internal energy with respect to the number of moles of substance I, holding temperature and pressure and all other substances constant. Likewise, the partial molar enthalpy is going to be defined as the partial derivative of enthalpy with respect to the number of moles of substance I, holding temperature and pressure and all other substances constant. And likewise, the partial molar Gibbs free energy is going to be defined as the derivative of the Gibbs free energy with respect to the number of moles of substance I, holding temperature and pressure and all other substances constant. This is also mu sub I, which we call chemical potential. We're going to be talking about chemical potential a lot later on. So this partial molar volume of substance, no, not volume, duh. The partial Gibbs free energy, partial molar Gibbs free energy, is going to be the most important one, as we'll see later.